So this is how we can split an 8-point sequence into 4 sequences where each sequence contains 2 samples. So the index values are 0, 1 in all cases. And we will take 2-point DFT of all these 4 sequences, and every 2-point DFT will produce 2 samples at its output. Now with the help of these 2-point DFTs, we will reconstruct the first 4-point DFT output. Similarly, with the help of these 2-point DFTs, we will reconstruct the other 4-point DFT output. So for that purpose, these 2-point DFT outputs will be used here for addition. Similarly, these 2-point DFT outputs will also be used here for addition. In a very similar way, the sample values produced by this 2-point DFT output will be used here for addition, and these sample values will also be used here for addition. Now, in order to get the 4-point DFT output, we have to use 4 total factors: W40, W41, W42 and W43. So W40 and W41 will be on the diagonal lines, and W42 and W43 will be on these straight lines, because half of the total factors will be on the diagonal lines and half of the total factors will be on the straight lines. And another way to understand this thing is, for this 4-point DFT, this is the first 2-point DFT box and this is the second 2-point DFT box. So total factors will be multiplied with those samples which are coming from the second DFT box. So these two diagonal lines and these two straight lines are coming from the second DFT box. That's why we have multiplied total factors with these lines. And similar is the case for this second 4-point DFT output. With the help of these two 2-point DFT outputs, we have reconstructed the second 4-point DFT output, which is represented by B0, B1, B2, B3. Now this is the first 4-point DFT output and this is the second 4-point DFT output. With the help of these two 4-point DFT outputs, A of K and B of K, we will reconstruct the overall 8-point DFT output as we did previously. So these 4 samples A0, 1, 2, 3 will be used here for addition. Similarly, these 4 samples B0, 1, 2, 3 will be used here for addition, and finally we can mark the total factors accordingly. W80, W81, W82, W83 will be on these diagonal lines, because these diagonal lines are basically the sample values B0, B1, B2, B3, and the last 4 total factors W84, W85, W86, W87 will be on these straight lines. So total factors will be multiplied with B of K DFT outputs. There will be no multiplication performed on the first 4-point DFT outputs, which were represented by A of K. So this is how we can implement 8-point FFT structure using 4 2-point DFTs and 2 4-point DFTs. Now we can split these 2-point sequences into 2 sequences where each sequence will contain only a single sample. So we will just left with a sequence containing a single sample like x of 0. Similarly, the second sequence will contain only x of 4. The third sequence will contain a sample value x of 2, and so on. So let's see how we can implement the FFT structure in that case where every sequence contains only one sample and we are required to take its 1-point DFT. And that FFT structure is so called full decimation in time, which means that we have decimated an n-point sequence into n number of sequences where each sequence contains only a single sample, and then we will take their single point DFTs. Now, before implementing that structure, we will first take a look at what is the meaning of single point or 1-point DFT. Now let's assume the time domain sequence contain only a single sample whose value is A, and we want to find what will be the output of single point DFT when we'll apply DFT analysis equation on this single point sequence. So this is the DFT analysis equation, and the value of small n will start from 0 and it will end at 0 because our sequence contains only one sample. And when we will put n is equal to 0 in the complex exponential function, it will become equal to 1. And what is x of n? X of n is just equal to a for n is equal to 0. So when we will multiply a with 1, we will get a as the output of single point DFT applied on the given sequence. So whenever we will take a single point DFT of a given single point sequence, we will get the same value as an output. So x of n and x of k both will be exactly equal. So let's start implementing the full decimation in time structure. Here, as you can see, we have represented an 8-point sequence into 8 sequences where every sequence contains only a single sample. The first sequence contains only x of 0 sample, the second sequence contains a single sample x of 4, and so on. And please remember that we are going to provide a scrambled order of samples to the input of this FFT structure. And how we have obtained that scrambled order? Basically, we have performed stage by stage decimation. We have made sequences of even and odd index samples. That's how we have obtained this order of samples which we are going to provide to our FFT structure. Now we are going to take 1-point DFT of all these single point sequences. So as we just discussed, when we'll take 1-point DFT of a single sample, we will get the same sample value in the frequency domain because x of k will be exactly equal to x of n. So when we will take 1-point DFT of these single point sequences, we will get the same value as an output. X of 0 will become x of 0, x of 4 will be equal to x of 4, and so on. So these are the time domain sample values and these are the 1-point DFT outputs which are exactly equal. Now our task is we have to reconstruct the 8-point DFT output, but that reconstruction will perform stage by stage. So this is the first single point DFT output and this is the second single point DFT output. With the help of these two 1-point DFT outputs, we will first reconstruct the 2-point DFT output. So in order to make a 2-point DFT output, this sample value will be used here, which is shown as a straight line, and this sample value will be used here in the form of diagonal line for addition purpose. But before addition, we have to use twiddle factor. So for 2-point DFT output, we have to use two twiddle factors which are W20 and W21. So W20 will be marked on this diagonal line, or in other words, x of 4 sample value will be first multiplied with W20 and then it will add into the x of 0 sample in order to provide the first sample value of this 2-point DFT output. Similarly, to calculate this sample value, x of 0 will appear as it is during addition operation, while x of 4 will be first multiplied with W21 and then we will add them. So the idea of the multiplication of twiddle factors is again same. Since for 2-point DFT output there are only two twiddle factors, so half of the twiddle factors, which means that the first twiddle factor will be on the diagonal line, while the remaining half, or while the for the second twiddle factor we will multiply this twiddle factor on this straight line. Similar is the case for the remaining 2-point DFT outputs. So at this point we will get the 2-point DFT output. Now with the help of these 2-point DFT outputs, we will reconstruct the first 4-point DFT output. Similarly, with the help of these 2-point DFTs, we will reconstruct the second 4-point DFT output, which are represented by A of k and B of k. And this structure is has already been discussed when we were reconstructing 4-point DFT output with the help of 2-point DFTs. Now, after getting the 4-point DFT outputs, with the help of these two 4-point DFT outputs, we will reconstruct the overall 8-point DFT output. So this is how we can implement the full decimation in time structure if the number of samples are 8. Now, since the single point DFT outputs are exactly equal to the time domain sample values, so there is no need to calculate them. And we can draw a simplified decimation in time structure like this one. So when we will write the time domain sample values at the input of FFT structure, these time domain sample values will also represent the 1-point DFT outputs. And this decimation in time structure is also called a butterfly structure, where a single butterfly operation is shown like this one. Now let's start solving a numerical example in which we are required to calculate 8-point DFT of the given analog signal using radix to FFT algorithm, and then draw its magnitude and phase spectrum. And the sampling rate is equal to 8000 samples per second. Now let's come to the solution. Since the given signal is in analog form, so the first step will be we have to make it discrete. So replace small t by nts. So the continuous time variable will become a discrete time variable. So just replace t by nts, and since fs is equal to 8000, so ts will become equal to 1 over 8000 seconds per sample. So just put the value of ts in both the components and we will get the x of n signal in the form of small n. Now we will find the sample values of this discrete signal. Since it is the case of 8-point FFT, so we are required to calculate 8 samples of the time domain sequence, which we will provide as an input to FFT structure. So we will put the value of n from 0 to 7 in this expression and we will get these sample values. And these are the total factors which will be used in the FFT structure. At the 2-point DFT stage, we will use W20 and W21, which are simply 1 and minus 1. At the 4-point DFT stage, we will use W40, W41, W42 and W43. And in the last stage where we will get the 8-point DFT output, we will use W80, W81, W82 and so on up to W87 total factors. The next step is to draw a butterfly structure for 8-point FFT, and in the first stage you will get the 2-point DFT output, in the second stage you will get 4-point DFT output, and the last stage you will get 8-point DFT output. And please note that we have to provide the input sample values in a scrambled order like x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. When we will provide the sample value input sample values in a scrambled order, then we will get the output sample values in a natural order from x of 0 to x of 7. So let's start with the first stage of computation where we are going to calculate 2-point DFT output. So when we will write these sample values will also represent the 1-point DFT outputs as we discussed earlier, because 1-point DFT outputs are exactly equal to the time domain sample values. Now we are going to calculate 2-point DFT outputs with the help of single point DFT outputs. So in order to calculate this sample value, we have to add two samples. One sample is this one, which is 0.3535, and the other sample is this 0.3535. But before addition, we have to multiply the second sample value or the second single point DFT output with a total factor. And in the 2-point DFT stage, total factors are W20, which is this one, and W21, which is this one. So here, instead of writing W20 and W21, I have mentioned their values, which are simply 1 and minus 1. So both methods are correct. You can write the total factors in the form of W notation and then you can refer their values, and the other method is you can write their values directly on the diagram. So in the 2-point DFT stage, I have written the values of total factors, while in the remaining two stages I have written the total factors in the form of W notation. So both approaches are correct. So 0.3535 plus 0.3535 into 1, which makes it 0.707. Similarly, 0.3535 plus 0.3535 into minus 1. So 0.3535 minus 0.3535 will make it 0. Now let's come to this output. How is it calculated? 0.6464 will appear as it is during addition, while minus 1.3535 will be first multiplied with 1 and then we will add them. So 0.6464 plus 1 times minus 0.3535, the answer will be minus 0.707. You can also verify it through your calculator. Now let's come to this output. Here we are adding 0.6464 and minus 1 into minus 1.3535. So uh, it is basically 0.6464 plus minus 1 into minus 1.3535. So the answer will be 2. Similarly, this sample is calculated by adding 0.3535 plus 1 multiplied by minus 1.0607. So the answer will be equal to minus 0.707. Now let's come to this output. Here we are adding 0.3535, which will appear as it is, and here we have to multiply minus 1.0607 with minus 1 before addition. So it will become 0.3535 plus 1.0607, which will make it 1.414. Now let's come to this sample. Here 1.0607 plus 1 into minus 0.3535. The answer will be equal to 0.707. Now let's come to this sample. 1.0607 plus minus 1 into minus 0.3535, and the answer will be equal to 1.414. So this is how we can calculate 2-point DFT outputs. Same concept will be applied for the 4-point and 8-point DFT outputs. So we will take some random sample values in order to get an idea about their calculation. So let's take an example of A of 0, how it will be calculated. To calculate A of 0, we again need two samples. One sample is this one, which is coming from the 2-point DFT stage. So 0.707 will appear as it is during the calculation of A of 0, while second sample is coming from minus 0.707. So minus 0.707 will be first multiplied with W40, and then we will add it with 0.707. So A of 0 will become equal to 0.707 plus W40 times minus 0.707, and please remember that first total factor value will always be equal to 1 angle 0, as we discussed in the previous lecture in detail. So the answer will be equal to 0 because 0.707 plus 1 multiplied by minus 0.707. So it will become 0.707 minus 0.707, which will make it 0. Now let's come to A of 3, how it is calculated. For A of 3, we again add two samples. The first sample is this one, which is 0. So 0 will appear as it is during addition, while the second sample is 2. So 2 will be multiplied with W43 before addition. So 0 plus W43 times 2 will be equal to 2 angle 90 degree. You can also refer the value of W43 from the total factors diagram. Now let's come to the B of 1 sample, how it is calculated. For B of 1, we have added again two samples. The first sample is this one, 1.414, which will appear as it is during addition, while the second sample is also 1.414, but we will first multiply 1.414 with W41, which is simply minus j in the rectangular form. So 1.414 plus 1.414 multiplied by minus j, and the answer will be equal to 2 angle minus 45 degree in the polar form, if you will express your result in the polar form. Now let's come to the B of 3 sample value. Here we are adding 1.414 and the other sample is also 1.414, but before addition we will first multiply 1.414 with W43, and W43 is simply equal to plus j. So 1.414 plus 1.414 times j will be equal to 2 angle 45 degree. You can verify it through calculator. Similar is the case for 8-point DFT outputs. Let's take two random sample values. For example, x of 2, how it is calculated. X of 2 sample value is again a summation of two samples. The first sample is coming from this first 4-point DFT output. So the first sample is 1.414 angle 0, which will appear as it is during addition, while the second sample is 1.414 angle 180 degree. But before addition, we have to multiply this sample value with W82, and the final result will be equal to 2 angle 45. Now let's discuss the calculation of x of 5. How x of 5 is calculated? It is again a summation of two samples. One sample, or the first sample, is 2 angle minus 90 degree. 2 angle minus 90 degree will appear as it is during addition. No multiplication will be done here. While the second sample, which is 2 angle minus 45 degree, will be first multiplied with W85 total factor, and then we will add them. And the final answer will be 0 angle 0. So this is how we can calculate the 8-point FFT output using radix 2 FFT structure. I will highly recommend you to solve 8-point FFT structure or to find the numeric values of the overall output directly on the diagram. There is no need to write their equations. You can solve them directly through calculator. You must have the values of the total factors which we have presented on the previous slide. So this is how we can calculate 8-point FFT of a given 8-point sequence. And here you can see the total number of unique components are again equal to n by 2 plus 1. So if the value of n is equal to 8, then 8 divided by 2 is 4, and 4 plus 1 is 5. So the first 5 sample values are unique, while the other half can be calculated by applying the idea of complex conjugates. So the mirror image of this component is present at this frequency value because it is equivalent to fs by 2. It is basically equal to n by 2 in terms of index value, and in terms of hertz value it is representing the fs by 2 point. So the mirror image of fs by 2 will be on the same value, while from now onwards we will fold back the spectrum. This value will be the mirror image of this value. So the conjugate of 0 angle 0 is 0 angle 0. The complex conjugate of 2 angle 45 is 2 angle minus 45, and the complex conjugate of 4 angle minus 90 is 4 angle 90 degree. While this is the DC coefficient, there will be no conjugate of the DC component. Here I have presented the equations of 4-point DFT outputs A0123, B0123, how they are calculated. So if you are facing any difficulty in understanding the calculation of those 4-point DFT outputs A of k and B of k, then you can refer these equations. Similarly, here the final 8-point DFT output calculations are presented in the form of equations from capital X of 0 to X of 7. So these equations are presented for your reference purpose, and these are the final DFT coefficients which are obtained through radix to FFT structure. And the advantage of expressing these coefficients in the polar form is that we can plot the magnitude and phase spectrum directly by looking at these values. So let's see how we can plot the spectrum. So this is the magnitude spectrum and this is the phase spectrum. Now in order to express the x-axis of both the spectrums in Hertz unit, we have to calculate frequency resolution, which is the ratio of fs and n. And fs was equal to 8000 samples per second and n was equal to 8. So frequency resolution will be 1000 Hertz. And the frequency value corresponding to these components will be 1000 Hertz, 2000 Hertz, 3000 Hertz, 4000 Hertz, and so on. Now, since fs was equal to 8000 Hertz, so we have to observe our spectrum up to fs by 2 only, which is 4000 Hertz in this case. And since the given signal was a real valued signal, so its spectrum will be a double-sided spectrum. So in the first half of a spectrum, which is from 0 to fs by 2, we will get the information of unique frequency components, which shows that our signal contains a 1000 Hertz frequency component and a 2000 Hertz frequency component. And their relative magnitude shows that the strength of the fundamental harmonic component is twice of the second harmonic component. Now let's come to the second half, which is from fs by 2 to fs. In this half, we will not get the information of any new harmonic components. These frequency components are essentially not representing 6000 and 7000 Hertz component. These spikes or these components are basically the mirror images of these components. So this component is basically the mirror image of 2000 Hz frequency component, and similarly this component is the mirror image of the 1000 Hz frequency component. So that's why we are observing the conjugate symmetry property in the FFT output, which is present in the second half of our spectrum. Now let's conclude this lecture on a very interesting technique, which is a bit reversal technique. And the idea of this technique is that, as we discussed in the derivation of radix to FFT, we have to provide a time domain sequence in an scrambled or in a shuffled order, like x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3, and x of 7. If we will provide the input sequence in this order, then we will get the output sequence in natural order, like x of 0, x of 1, x of 2, and so on up to x of 7. So the question is how we can obtain this shuffled sequence, or in other words, in what particular order we have to provide a time domain sequence to our FFT structure. So one possible method in order to get this shuffled or time domain sequence is that we can perform stage by stage decimation, or in other words, we can make smaller sequences by collecting even and odd index samples in every stage. But this process might be very time consuming if the value of n is very high. As you can see, if the value of n is equal to 8, as we discussed in our derivation, then after 3 stages we obtain this order. And let's assume if the value of n is equal to 1024, then it means that we can obtain this shuffled order of time domain sequence after performing 10 stages. So our objective is we have to shuffle our data through a technique, and the name of technique is bit reversal. So let's see how the bit reversal technique will work. Now let's perform data shuffling through a bit reversal technique for an 8-point FFT. As you already know, when we collect data through ADC, the natural order of index values are 0, 1, 2, 3, and so on. Now, as you can see, the name of bit reversal technique shows that we have to reverse the binary bits. So the first step is to represent these 8 numbers in the binary form. And in order to express these 8 numbers, we will need a 3-bit binary number. So this is how we can represent these 8 numbers in a 3-bit binary number: 000, 001, 010, and so on. Now we are going to reverse these binary bits. So by reversing the binary bits, we will get these reverse binary bits. 000 will remain 000, 001 will become 100, 010 also remain 010, 011 will become 110, and so on. So this is how we can obtain reverse binary bits. Now the last step is we have to represent these binary bits in the form of decimal numbers. So 000 will be 0, 100 will become 4, 010 will be 2, 110 will be 6, and so on. So this is how we have obtained the required shuffled order index values 0, 4, 2, 6, 1, 5, 3, 7. And the advantage of using bit reversal technique is that there is no need to perform stage by stage decimation in order to get the required scrambled order index values. We can just perform bit reversal technique. So in simple words, bit reversal technique can be used in place of decimation in time. So that's it for this lecture. In the next lecture, we will perform computational analysis of the radix to FFT structure. Until then, thank you very much and Allah Hafiz.